Hello, this is Richard Rood, and this is a module in my course on climate change science and climate change problem solving. This particular module is going to be an uncertainty discussion, and in order to anchor that uncertainty discussion, I'm going to use plots of the global temperature until 2100. So I'm going to be looking at some time from the past till sometime in the future, and that time in the future is the year 2100. The source of these plots are going to be from the Intergovernmental Panel on Climate Change, which assesses the state of the knowledge about climate change on time periods of about 5 to 6 years and produces these comprehensive reports, which include a summary for the policymakers, which I have provided information or links to in the lecture. I'm going to look at the third, fourth, and fifth assessment report. There are two reasons I'm going to look at essentially the same type of plot in three assessment reports. One is because the same sort of form and the same sort of information is present in all of them, though with different details, perhaps different clarity about how the uncertainties are represented. The other is what you'll see over this time period of about a decade and a half now, is that the results are pretty much the same from one time period to the other, that the climate, the global surface average temperature, is warming. So this is the plot from the assessment report, the third assessment report that was published in the year 2001. And at this point, all I want to do is describe what is in these figures. So in all these figures on the axis here at the bottom, the x-axis, is time. And this time axis, in this case, goes from the year 1000 to the year 2100. On the y-axis here is temperature, and this is temperature in degrees Celsius. It is a deviation from some sort of reference value so that it is showing variations of the Earth's temperature from that reference value. And in this figure, it's from 1990 value. So what is the surface temperature that's shown here? So this is the surface air temperature. So this is the temperature of the air at some level above the surface, which is generally taken to be a standard of 2 meters or about 6 feet. That is the temperature that, say, a human would experience in their day-to-day activities. This is the same sort of figure from the 2007 assessment. It differs in details in a number of ways that I will not belabor here. It goes from 1900 to 2100, and here again is the warming. And you can see that in the past we were below this zero line, and in the future we're going above this zero line. And then here's a figure from 2013. The fifth assessment report. Again, there are details that have changed. It's 1850 is one, but as we have moved to the 2007 and the 2013 reports, rather than having observations back here, we now have model simulations back here. And the decisions to change these details were often made in consideration of what is the message that needs to be conveyed and the experience that the field has learned over the years of trying to convey these messages. In all cases, I think it is correct to say these are complex graphs that are full of information. So I want to go back to the first figure, and one of the reasons I like this figure is what is shown back here is based upon observations. I can introduce the concept of observational error or observational uncertainty. So in this first part of the graph, we have observations that are from proxy data, and they're of only the northern hemisphere. This is where we have information from the explorations that are associated with Europeans, from the Chinese civilizations. We have collected information that are proxies of what the temperature of the Earth is like. And those proxies are often tree rings, sometimes they're ice cores, sometimes they're based on lake sediments. There are many ways that we know that we have some sort of proxy that is a representation of temperature. What you can see here in the red line is an average. It's a time average, and surrounding that red line are these gray spikes, this gray envelope. And that gray envelope is a measure of the uncertainty, and that uncertainty comes from two places. One is the error associated with the method itself, a measurement error, and the other is the representation. That is, how representative, how much information do we get about, say, in this case, the entirety of the northern hemisphere rather than just one point. There are two major sources of observational uncertainty there, one associated with the actual measurement method and the other being associated with the representation of the measurement. If we move to this time, we're still looking at observations, but what has happened is the invention of the thermometer, so that we're starting to see that in addition to the proxies, we have what we would call a more direct measurement or an instrumental measurement of temperature here, and we see that the uncertainty goes down, the width of the envelope goes down. And then here in the mid to late 1800s, we see another reduction. And that other reduction is due to the expansion, really, that's associated with the Industrial Revolution and the colonization of the world, and really the European colonialization that sent temperature measurements, sent thermometers all over the world, and hence, in support of commerce and military activity, we started collecting more and more weather data. For the climate scientists, this again reduced the uncertainty associated with the temperature, both in terms of the representativeness as well as in terms of the quality of the observations. And then in this little line here is where we see the satellite observations becoming an important and indeed dominant source of temperature information in some cases. And at that point, the uncertainty associated with our knowledge of the Earth's temperature becomes really quite small. Within this observational record, we see what I would call the second type of uncertainty in this discussion, and that's that associated with natural variability. So the natural variability includes things like El Nino and La Nina, which is an exchange of heat between the ocean and the atmosphere. But we're more familiar with variability, say, associated with the seasonal transition from winter to summer, or with weather patterns, where there are times when we have hot spells, with times we have cold spells, heat waves, cold snaps. Those are periods when, say, the weather is in some sort of persistent pattern. Another source of natural variability would be volcanic eruptions, and another source would be changes in the sun associated, for example, with sunspot cycles. So from a climate perspective, this natural variability is full of opportunity to understand cause and effect and processes. But from a climate change perspective, this is a type of noise, and if you're looking for a signal of global warming, of changes in the Earth's surface temperature, then you have to evaluate any changes that you might see relative to these bumps and wiggles, which represent the natural variability. So the third type of variability that I want to discuss, the third type of uncertainty that is present in this figure, is what I'm going to call scenario uncertainty. And if you look over here, you see these types of scenarios that are represented with different colors and different dots and dashes. And what those scenarios are different representations of the future. So they have considerations about population, they have considerations about carbon dioxide emissions, considerations about policy, and the sorts of things that we might do. The bars in here show a range that is associated with each scenario, and that range associated with the scenario is the range that is associated with models. So there's an ensemble of models, and that would be called the model uncertainty. So we see here, looking into the future, these sort of two major types of uncertainty. One, the model uncertainty, which causes a range within any particular scenario. And then if we look from top to bottom, here we see the uncertainty that's associated with all of these different scenarios and the model uncertainty associated with each scenario. You get this very wide range of uncertainty, this gray around here, which represents this totality of this scenario uncertainty and this model uncertainty. So we've moved from observational uncertainty with natural variability to this combined uncertainty about the future that's wrapped up in the model scenario and in the scenario uncertainty. And there's still natural variability in here, but these models are averaged together such that these natural sources of variability tend to be averaged out. And so when we start to look for changes in the global temperature, we're going to be looking for temperature signals that are larger than this natural variability. It's important to notice at this point in time that no matter what scenario we choose and what the model uncertainty is, we are looking at warming of some sort. We do not see situations with increasing carbon dioxide where we are going to see global temperature decrease. So the signal that the planet will warm is really quite robust. There's a lot more uncertainty and argument about how much the planet would warm, which is represented by this range here. I wanted to go back to this figure because this figure, I think, shows the model uncertainty a little bit more clearly. Again, we have scenarios here, and then around each scenario you see this colored envelope. And so in this version of the figure, it shows the range for each scenario of all the models, and you can see here's the scenario uncertainty perhaps that's associated with all the scenarios represented by this envelope here. With that, here's a summary of the uncertainty types that are discussed here. One is the observational uncertainty. How accurate are the observations and how representative are the observations? The second is the internal variability, which is often caused by natural sources such as seasonal cycles, patterns of weather, exchange of heat, for example, between the ocean and the atmosphere, and then changes in the sun, solar variability, and volcanic eruptions are other sources of natural internal variability. The next type of uncertainty is that associated with scenarios, which are wrapped up in this idea of future emissions and more generally land surface changes and the things that we as humans are doing that change the temperature of the earth. These are wrapped up in things like policy, population, and technology, which, of course, if you imagine thinking about the future, we don't know these things that well, so we make projections based upon a variety of knowledge or scenarios about what we think the future will be. And then we add to that the intrinsic uncertainty that is associated with these tools, these models to predict the future, to project the future, which is based upon how well do the observations describe what needs to be modeled, that is, how well do we understand the physical system, and then how well do the mathematical equations represent those observations in the climate and the physics, the chemistry and the biology, which determine cause and effect, and then how well are the mathematical equations represented on the computer. And there will always be uncertainties. Uncertainty is part of the scientific method of exploration. Science does not produce facts, it produces knowledge with a description of the uncertainty associated with that knowledge. And with that, I will conclude this description of uncertainty, and thank you for your attention.